Hello and welcome back to your Chem 4 lecture. We are in lecture 10, and we're going to continue talking about acids and bases by discussing the equilibrium between acids and bases. As it turns out, acids and bases, as we mentioned, are extremely important to understand for all sorts of biological reasons. Okay, so now one thing that we need to keep in mind is that there's like a new kind of principle here. We've been talking about forward reactions and reverse reactions for a lot of these weak acids and weak bases, for example. And anytime you have a forward reaction and reverse reaction that can take place at the same time, you have a system that's at what's called equilibrium. So for an equilibrium reaction, two reactions actually take place at the same time. There's a reversible reaction that proceeds in the forward direction and in the reverse direction simultaneously. So one example is the dissociation of HF, which is a weak acid, like we discussed in the last lecture. So HF dissociates into the fluoride ion and the hydronium ion by giving up its proton to water. That's the forward reaction. The reverse reaction occurs as well, where now the conjugate base reacts with the hydronium ion as the conjugate acid to reform the original acid, hydrofluoric acid, and the original base, water. Okay, now equilibrium is a state where after you let a reaction go for a while, eventually the concentration of reactants will decrease and the concentration of the products will increase until they hit a steady state. And that steady state is what's known as equilibrium. And once again, this should be forward. I thought I fixed this, but apparently there's some problem displaying this. You have a forward arrow and a reverse arrow to show that both reactions are occurring at the same time. So again, at equilibrium, the concentration of reactants and concentration of products are both constant, and also the rate of the reactions are the same as well. So essentially, the rate of the forward reaction equals the rate of the reverse reaction. That's why basically as many HF are giving up protons, the same number of F- are picking up protons to form HF, hence no net change in the concentration of either the reactants or the products. So what do I want to say here? So I feel like I maybe missed something here. Again, when you start the reaction, you have a certain number of reactants, and those are going to quickly react until you reach equilibrium, and then they're going to slow down. The way you can think about it is basically, think about it this way. If you just have HF in an aqueous solution, then the HF can give up protons to form F-, but if there's no F- around, then the F- can't do the reverse reaction. So only after a certain amount of time, after you've formed concentrated products, then all of a sudden, now the reverse reaction can take place. And finally, eventually, those rates are going to equal out. So eventually, the rate of the forward reaction is going to be very fast, and the rate of the reverse reaction is going to be very slow until you hit equilibrium, at which point both of them equalize. Okay, so here we go. We can complete each of the following with either equal or not equal, faster or slower, or change or do not change. So before equilibrium is reached, the concentration of the reactants and products, this is kind of confusing, but basically do they change or do they not change? And note, this is before equilibrium is reached. Okay, so before equilibrium is reached, the concentration of the reactants and products change. You know that the amount of the reactants is going to decrease and the amount of the products is going to increase. Okay, initially the reactants have a rate of reaction blank than the rate of the reaction of the products. So is it faster or slower for the forward reaction compared to the reverse reaction? So initially, when you just first put it in there, all you have are reactants. So the forward reaction is going to be faster than the reverse reaction, so it should be faster. At equilibrium, the rate of the forward reaction is blank than blank to the rate of the forward reaction. Is it equal or not equal? Well, at equilibrium, by definition, the rate of the forward reaction is equal to the rate of the reverse reaction, so that should be equal. And then finally, at equilibrium, the concentrations of reactants and products, do they change or do they not change? And the answer is they don't change. They hit equilibrium and the concentrations stay the same. Sorry, now that was a little bit of a confusing introduction to equilibrium, but let's try to have some fun with it. This is actually kind of a fun part of the chemistry semester, which is Le Chatelier's principle. One kind of consequence of having these equilibrium reactions is that if you alter the concentration of a reactant or a product when you have it at equilibrium, the rates of the forward and reverse reactions will change. Basically, depending on how you modify the equilibrium system, the reaction is going to respond to it by trying to get back to equilibrium. So this is Le Chatelier's principle. When equilibrium is disturbed, the rates of the forward and reverse reactions will change to relieve that stress and again reestablish equilibrium. So for example, if you have two tanks that are connected, at equilibrium, the water levels should be equal. So tank A and tank B both have the same amount of water when you put it in there. Now, if you just add water to tank A, you will have basically an overall greater balance of water in A than in B. So what happens? Well, the rate of water flowing from A to B is going to increase, and the rate of water flowing from B to A is going to decrease until eventually you hit equilibrium once again. And now the rate of water flowing from A to B is the same as the rate of water flowing from B to A. So this is an example of Le Chatelier's principle. Okay, so gosh, I'm going to have to do this a million times here, but let's go ahead and draw in these reversible reaction arrows. Okay, so given this reaction here, where we have HF plus H2O forming fluoride and the hydronium ion, if we were to add more HF, what would happen to this equilibrium? So if we're starting from equilibrium and we add HF, what's going to happen? Well, we increase the concentration of the reactant HF. So what can happen to balance that out? We're going to send this out of equilibrium. Well, what the reaction is going to do to reduce the concentration of HF is it is going to increase the rate of the forward reaction. So when we add HF, now all of a sudden the forward reaction is going to happen faster to give us more of the fluoride ion. So again, Le Chatelier's principle will tell us that adding more reactant will cause the system to shift the direction towards the products until you get to equilibrium one more time. Okay, now what if we had a reactant that reacted with the HF and so removed it and decreased the concentration of HF? Well, if you decrease the concentration of HF, that puts a stress on the system, and the reaction is going to try to, so we're going to decrease the concentration of HF this time. What the system can do then is, if you remove HF, there's more fluoride ions bouncing around with hydronium ions, and more fluoride is going to pick up hydronium ions to form HF to basically counteract the stress that was put on the reaction. So again, by removing the reactant, we actually increase the rate of the reverse reaction, and in so doing, shift back towards equilibrium. Oops, hold on, let me clear those annotations again. Okay, so now if we add more F minus, what's going to happen? So if we increase the concentration of F minus, that puts a stress on the system and takes it out of equilibrium. What can we do to consume that F minus? Well, if the reverse reaction increases in pace, more F minus is consumed, producing more HF. So if we increase the concentration of a product, we're going to increase the rate of the reverse reaction. Okay, so these are the general changes that we're going to see when we have an equilibrium system. If we add a reactant, then the Le Chatelier's principle tells us that the forward reaction rate will increase, and so it shifts the equilibrium in the direction of the products. If you remove a reactant, on the other hand, that decreases the forward reaction rate, so the reverse reaction rate will increase, and therefore the shift is going to be towards the reactants. If we add a product, that is going to increase the reverse reaction rate, and so you're going to shift again towards the reactants. And then finally, if you remove a product, it decreases the reverse reaction rate, and so what's going to happen is if you remove that product, the forward reaction is going to fill in the gap that you just made. Okay, now this is linked to health very closely because hemoglobin and the oxygen transport system in the human blood is very sensitive to equilibrium shifts. Certainly when hemoglobin touches oxygen, oxygen sticks on hemoglobin and forms oxyhemoglobin. Now, it doesn't stick there permanently, right? I mean, obviously that would be bad. The oxygen gets released into the cells where it's needed. So when you have an O2 level that's high in your lungs, for example, you shift the direction towards the product, oxyhemoglobin. Then in the tissues where the oxygen is supposed to be delivered, the concentration of O2 is very low. So there, the reverse reaction occurs, and you actually release the molecular oxygen, which can then be used by the body. Okay, now let's say that you're climbing a mountain, a really high mountain, and once you hit 18,000 feet, you get 29% less oxygen. And so you can have this experience of what's called hypoxia, or not enough oxygen. Hypoxia is characterized by increased respiratory rate, and that gives you symptoms like headaches, decreased mental acuity, fatigue, and low physical coordination. This makes sense because with Le Chatelier's principle, if we decrease the concentration of oxygen, we would see a shift away from oxyhemoglobin in the blood, which is the problem, which is where we want it to be. Okay, so let's go ahead and give it a shot. Here, let me draw in the reaction arrow again, forward, reverse. Okay, so a really important reaction for the body is the reaction of carbonic acid with water. So carbonic acid reacts with water as a weak acid, forms the hydronium ion and the hydrogen carbonate ion. Okay, so using the Le Chatelier's principle, like what we've talked about, predict whether the system will shift in the direction of the products or the reactants. In other words, will you have a shift in the increase of the forward rate or an increase in the reverse rate? If you increase the forward rate, then you shift towards the products. If you increase the reverse rate, then you shift towards the reactants. I hope that makes sense. Anyways, for this sample exercise, what I want you to do is use Le Chatelier's principle to determine whether the system will shift towards products or towards the reactants for each of these changes. When you're adding carbonic acid, if you're removing hydrogen carbonate, and if you're adding hydronium ion. So go ahead and give it a shot. Pause the video here, try to puzzle this out, and then we'll look at the answers when we come back. Okay, so let's go ahead and look at the answer. So if you add carbonic acid, that means you're adding in a reactant. If you increase the concentration of the reactant, the forward rate is going to pick up, and so the equilibrium will shift towards the products. If you remove some hydrogen carbonate, that means you're removing some of the product. And in order to resist that change, the forward reaction will increase to basically fill in the hydrogen carbonate that you're losing. So it shifts again towards the products. Finally, if you add in hydronium ion, well, the hydronium ion is a product. So if you add in hydronium ion, the reaction or the equilibrium system will work to counteract that change. And so the reverse reaction will increase. In other words, shifting towards the reactants. Okay, so that's equilibrium. And the reason that this is really important is because we need to be able to understand equilibrium reactions in order to understand the dissociation of water. And this is key for our understanding of pH. So that's what we're going to talk about now. Okay. So in the dissociation, okay, so starting from water. Water we've seen act as a Bronsted-Lowry acid, and we've seen it act as a Bronsted-Lowry base. This property of water is known as amphoteric. So because water can act as an acid or a base, it is amphoteric. And so in water, when you have two water molecules that hit each other, you can have this reaction occur where a proton can be transferred from one H2O molecule to another. One molecule acts as the acid, the other one acts as the base. And you have an ultimate equilibrium that's released between the conjugate acid and conjugate base pairs. So we finally got our reaction arrows working. So let's see if this is working. So you have two water molecules as the acid and as the base. The one that accepts the proton becomes the hydronium ion. The one that gives up the proton becomes the hydroxide ion. Okay. Oops. Okay, we lost it again. Okay. Now, this reaction is a very special reaction called the water dissociation reaction. So this gets to equilibrium. And one of the things is because in pure water, all you have are the water molecules, you know that the concentration of hydronium ion has to equal the concentration of the hydroxide ion. And so we can measure that, in fact. And when we do, we find out that in pure water, at 25 degrees Celsius, the concentration of both hydronium ion and hydroxide ion are 1.0 times 10 to the negative 7th molar. So we can come up with a constant calculation, which is the Kw. This is the water dissociation constant. And the water dissociation constant is equal to the concentration of hydronium ion times the concentration of hydroxide ion, which if we just plug in 1.0 times 10 to the 7th for each of these, comes out to 1.0 times 10 to the negative 14th at 25 degrees Celsius. So this is going to be our kind of guiding light here. And this is going to be provided for you on the test. Kw equals hydronium ion times hydroxide ion, and that equals 1.0 times 10 to the negative 14th. Oof, sorry, that is gross. Okay. All right. So now what does this all mean? Well, we know that always the concentration of hydronium times the concentration of hydroxide is going to be equal to 1.0 times 10 to the negative 14th. That's for pure water, that's for acid, and that's for base. All the time, that's always going to be the case. Now, the difference between acids and bases is going to be basically the concentrations of hydronium hydroxide ion in solution. If you have a greater concentration of hydronium ion than hydroxide ion, then you have an acidic solution because hydronium ion is an acid. If you have the hydroxide ion concentration greater than the hydronium ion concentration, then your solution is basic. And of course, if they're equal, that's when you have a neutral solution, although that only happens at one specific concentration. Now, pure water, totally neutral. We already covered this, right? If you have a pure water sample, you have a concentration of hydronium ion equal to 10 to the negative 7th molar and a hydroxide ion concentration of 10 to the negative 7th molar. Perfectly neutral. Now, if you add an acid to the water, all of a sudden, you're going to have the water molecules accepting protons from the acid. That increases the concentration of the hydronium. Now, that means that the concentration of hydronium ion will exceed 1.0 times 10 to the negative 7. To counteract it, the concentration of hydroxide ion will decrease. Because remember, we're still stuck with this, the Kw, which we know the Kw is equal to 1.0 times 10, and apologies that this is going to be a little sloppy there, times 10 to the negative 14, which equals the hydronium ion concentration times the hydroxide ion concentration. Oops. There we go. So if the hydronium ion concentration increases, the only way that the hydroxide ion can kind of like balance it out and keep this Kw expression true is by decreasing. That gives us an acidic solution. Okay, next up, basic solutions. This is the opposite, where we increase the concentration of hydroxide ion, which causes that to exceed 1.0 times 10 to the negative 7th molar. And the only way that the hydronium ion can react is by decreasing in concentration. Because we know if we increase this concentration, we know this times this has to equal 1.0 times 10 to the negative 14. So this concentration has to decrease. So if we have the hydroxide ions greater than 1.0 times 10 to the negative 7th, then we know that that's a basic concentration. Similarly, we can also say, oh, the hydronium ion concentration is less than 10 to the negative 7, so it must be basic as well. So that's how it works. Basically, neutral solution, the concentrations are equal. Acidic, that's where the concentration of hydronium is greater than the concentration of hydroxide, and also greater than 10 to the negative 7th molar. And basic is opposite, where the hydroxide ion solution is greater than 10 to the negative 7th, and also greater than the hydronium concentration. Okay, so here's how that math actually works. Let's take a look at some example solutions here. So if you have an exactly neutral solution, you know that you have to have 1.0 times 10 to the negative 7th molar for both the hydronium ion and the hydroxide ion. Now note, all of these have the Kw equal to 1.0 times 10 to the negative 14th. In other words, for each of these examples, you can take this number times this number, and it has to equal this number. That means even if we're only given one of these columns, we can solve for the other column using our equation. Now, if you have 1.0 times 10 to the negative 2 molar for hydronium ion, that's greater than 10 to the negative 7, so that's going to be an acidic solution. Same thing here, 2.5 times 10 to the negative 5th molar acid concentration. That is, again, greater than 1.0 times 10 to the negative 7th, so that's an acidic solution. For the basic concentrations, for example, if we have 1.0 times 10 to the negative 6th molar hydroxide ion, that's greater than 10 to the negative 7th. So again, that is also basic in this case. And then finally, 10 to the negative 4th being greater than 10 to the negative 7th, that is also basic, because that's the hydroxide ion. Okay, so now I've hinted at this already, but if we know the concentration of hydronium ion in solution, we can calculate the hydroxide ion concentration using the Kw. Also, if we know the hydroxide ion concentration of a solution, then we can use Kw to calculate the hydronium ion concentration. Given the fact that the Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, you can either do the algebra for hydroxide ion concentration, which would be equal to Kw divided by hydronium ion concentration, or the concentration of hydronium ion would be equal to Kw divided by the concentration of hydroxide ion. Okay, so here's an example of how we could use this. Ask yourself, what is the hydronium ion concentration if the hydroxide ion concentration is 5.0 times 10 to the negative 8? Well, this is a simple substitution problem. We know that the Kw is 1.0 times 10 to the negative 14th, and we know now the hydroxide ion concentration is going to be equal to 5.0 times 10 to the negative 8. If we just substitute this number in for our hydroxide ion concentration, then all we have to do is calculate the hydronium ion concentration through some simple algebra. This becomes 1.0 times 10 to the negative 14th divided by 5.0 times 10 to the negative 8, which would give us an answer of 2.0 times 10 to the negative 7th molar. Now, is that acidic or basic? Well, 2.0 times 10 to the negative 7th molar is greater than 5.0 times 10 to the negative 8th molar. So that tells us the hydronium ion concentration is greater than the hydroxide ion concentration. So the solution is acidic. Okay, let's go ahead and give it a shot here. If lemon juice has a hydronium ion concentration of 2.0 times 10 to the negative 13th molar, what is the hydroxide ion concentration of that solution? Go ahead, pause the video here, come up with your answer, and then we'll look at the answer when we come back. So go ahead, pause. Okay, and let's take a look. Well, step one, we're given the hydronium ion concentration, and we need the hydroxide ion concentration. So clearly we need to use our Kw expression to solve it. And we know that the hydroxide ion concentration is equal to the Kw divided by the hydronium ion concentration. Well, plug in our number here. Our hydronium ion concentration, 2.0 times 10 to the negative 3rd, Kw, 1.0 times 10 to the negative 14th, divide it out, and you get 5.0 times 10 to the negative 12th. So here, the solution becomes the solution is 5.0 times 10 to the negative 12 molar, and clearly having such a low concentration of hydroxide ion and such a high concentration of hydronium ion, that tells us that we have an acidic solution. Okay, and that's all we have to do for now. In the next lecture, we'll talk about pH and then some reactions that acids and bases go through. But until then, I will see you soon, and I will talk to you very soon. Bye-bye.